Dear students, in this video we will discuss about diesel cycle and its working. So the diesel cycle, which was devised by Rudolf Diesel in 1892. So three auto cycle which is working on the petrol and the diesel cycle which is using the fuel as the diesel, but the heat addition takes place at a different condition. While the heat addition in the Otto cycle takes place at constant volume, here in the diesel cycle, the heat addition takes place at constant pressure. The fuel used in this cycle is also different. It is the diesel fuel. The suction of the air only takes place in case of the diesel cycle, while in case of the Otto cycle, the suction of air and fuel mixture takes place in the Otto cycle. At the end of compression, here we use a fuel injector with the help of which at the end of compression diesel fuel is injected. So when the fuel is injected, its compression ignition takes place. So we should keep in mind Rudolf Diesel. This is the scientist who devised this cycle. Rudolf Diesel devised this cycle. And the year in which it was devised it is 1892. So it is also having the four processes in which two processes are the isentropic compression and isentropic expansion, and one constant volume process and one constant pressure process. The heat addition here takes place at constant pressure and the heat rejection takes place at constant volume. So we can represent this cycle on the TB and TS diagram. So first we say, or we can write here for the diesel cycle. We say our diesel cycle. And this diesel cycle consists of four processes. Diesel cycle, and we can write here its processes. So let these are the four processes which are used in the diesel cycle. First process, you can say it is the 122. 122 is the isentropic compression of atmospheric air. Isentropic compression of atmospheric air. In the second process is 2 to 3, which is the constant pressure heat addition. This process is constant pressure heat addition. Process 3 to 4 is isentropic expansion. In this, the power is received from the cycle. This is isentropic expansion process. And 4 to 1 process, constant volume heat rejection. So these processes now can be represented in the PVLDA diagram. You can draw first PV diagram, pressure volume diagram. In this vertical axis, we are showing the pressure P. In this horizontal axis, we are showing volume D. So the first process is isentropic compression. So we can represent isentropic compression as that this is 1 to 2. This is the isentropic compression of the atmospheric air. This is 2 to 3. At this point is 3. So 2 to 3 is constant pressure heat addition. 1 to 2 isentropic compression. So here the entropy remains constant. We can write S equal to constant. Then 2 to 3 is constant volume heat addition. This is constant volume, sorry, constant pressure heat addition. Constant pressure heat addition. Then 3 to 4 is isentropic expansion. This is 3 to 4 isentropic expansion. So we write here S equal to constant. Constant. This point is 4. In this 4 to 1 is constant volume heat rejection. So here is 2R. Here the volume D4 equal to G1. Our volume remains constant. This is the volume. Volume is G2, at which point 2 the fuel injection start. And this volume is G3. Actually, at point 3, the heat injection stop. So the point 3 is also called as cutoff point. It's called as cutoff point because fuel injection stops here. It's called as cutoff point. So this is the representation of the diesel cycle on PV diagram. The same cycle can also be represented on the TS diagram. is also draw. It's a TS diagram. In this vertical axis, there is the temperature. Horizontal axis, there is the entropy. So the first process is 1 to 2. It is isentropic compression. So we can draw a vertical line showing the isentropic compression. So that this is point 1, here the compression starts, and point 2, here compression of the air ends. Then this is the isentropic process. We write here as equal to C, the constant enthalpy process. Then process 2 to 3, it is a constant pressure process because here the heat addition takes place at constant pressure. The heat addition is there, QA, and because it is a constant pressure process, so we write here P equal to constant, P equal to C. At this point is 3. Then 3 to 4, which is on the previous PV diagram also, 3 to 4 is isentropic expansion process. It is at the constant entropy. This point is 4, and this 4 to 1 is a constant volume heat rejection. So this is V equal to C, constant volume process. And the heat rejection takes place here, to be right here. This is the QR. 4 is isentropic expansion process. So in the process 1 to 2, this is the isentropic expansion, isentropic compression. So entropy remains constant, which is S1 is equal to S2. And in this process 3 to 4, again this is the isentropic expansion process. Here entropy remains constant, here is 3 is equal to S4. This is the completed TS diagram. Now we start this cycle from point 1, considering point 1 because this is we say it is the BDC, it is the BDC position. This is the BDC position of the piston, and at point 2 it is the TDC position. Here it is TDC. So considering the piston is at BDC position, it means the suction of atmospheric air has already been taken place. Now the piston will start moving from BDC to TDC, because in the diesel engine or the diesel cycle, the suction of atmospheric air only takes place when the piston starts moving from point 1 to point 2. There is the isentropic compression of the atmospheric air. The pressure will increase from pressure P1 to P2, and also the entropy will remain constant on the TS diagram from S1 to S2. At the end of compression at point 2, when the pressure has been increased considerably and it is enough to ignite by the compression to the diesel fuel, the fuel is injected at point 2. When the fuel is injected, the combustion of the diesel will take place, and from point 2 to point 3, it is the constant pressure heat addition. So the combustion will take place. Definitely it will increase the pressure and temperature, but the expansion of this combustion gases, there will also be slightly decrease in pressure. So the pressure remains constant from 2 to zero point 0.3. So during this stroke 2 to 3, pressure remains constant, and fuel injection start at zero point 0.2 and fuel injection stops at zero point 0.3. So zero point 0.3 is called as the cutoff point. 0.3 is called as the cutoff point. This 0.3 is called as cutoff point. After that, in the process 3 to 4, this is the isentropic expansion of the cycle. So in this cycle, because of the high combustion and high pressure and temperature of the fuels, combustion gases, they will push the piston and the piston will move in the VDC position. So in this 3 to 4 process, the power is received from the cycle. At 0.4, now the 4 to 1, the last process will occur. So in this process, because inlet valve is already closed, the outlet valve will open and the piston, and because of this, actually it is a replacement of the smoke by the fresh air mixture. So the heat rejection is not shown on this cycle, but it is simply replaced by the heat rejection. So 4 to 1 is a constant volume heat rejection, means the substitution of the smoke or the combustion gases by the fresh air. So in this way, this cycle is completed. In this cycle, no spark plug is used. We use the fuel injector for the injection of the fuel. So this diesel cycle, also called as the constant pressure heat addition cycle. Diesel cycle called as constant pressure heat addition cycle. Constant pressure heat addition cycle. The engine working on the diesel fuel is also called as CI engine, or we can say it is the compression ignition engine. Compression ignition engine. Or CI engine. This is all through the presentation, presentation of the dual cycle in the previous diagram. Next, we will discuss the efficiency of dual cycle in our next lecture. Thank you.